Hello, everyone. We're going to be talking about our very last three sections of the statistics module. Just wanted to um, talk a little bit about topics 7 and 8 from last week, and want to make sure you guys are paying attention to the videos, which clearly is not the case for some of you guys. This is the data for all of the students that have worked on topic 7 and 8 up through it's currently 1:30 p.m. on Friday afternoon, um, the 24th. And if you look over here, one thing that you do notice, I have filtered out all the 100 grades. Um, and you don't see any of the names over here, but I'm just showing you what sort of data Algebra Nation gives me. It tells me exactly what time a student started um, the check your understanding questions. This particular student started at 2:28 in the afternoon. That's what 14:28 is, military time, on the 16th, and they finished at 14:36. So that's about 5 minutes or a little bit less than 6 minutes. And they got a zero and so on. Now, this might actually be the same student with a 0 minute. They started immediately after they finished this attempt. They started a second attempt and they got two of the three questions right. Okay. Um, but what is interesting to me about this? Well, at the end of the video last week, I actually walked through every single question and told students exactly what the correct answers were for all of topic 7 and all of topic 8. There should be no zeros and 33s and 67s whatsoever if you were watching the videos. Now, I know the videos are long, guys. They, by nature, they have to be. I'm doing a one single video for the entire week kind of a thing. So if the video is an hour long um, and you spend an hour watching that video and taking notes down, and then you spend, I don't know, maybe 20 minutes to 30 minutes on each check your understanding section, you're talking about maybe 2 hours, 2.5 hours for the entire week. I don't think compared to the amount of time you used to have in my class, 47 minutes, 5 days a week, I don't think that's too much to ask. Um, so, guys, it's clear to me that some of you guys are doing the right thing, um, watching the videos, seeing what's going on. Of course, this isn't everybody. We still had a lot of people that had 100s. If I bring up all the grades, you can see that there's a lot of 100s in there. But again, some of these 100s are fake. Um, you get the whole 0 100 thing going on for certain back-to-back topics, that kind of thing. But I'm not going to do that this week with showing you exactly how to answer the questions, but there is one of the questions that had, I think, a bad answer. So we'll talk about that when we get to it. Um, anyways, just guys, again, please pay attention to the videos. Make sure your first attempt at each of the check your understanding questions is a valid attempt. Take your time, work your way through it. Um, Make sure you're trying to learn this stuff, especially if you're planning on going on to AP statistics. A lot of what we've been talking about is the kind of stuff we do, which is another class I teach. So if you're interested in that class, be on the lookout for when it's time to sign up for math classes next year. Okay, so we're going into section 12, topics 9, 10, and 11. And what we're trying to do here, this is called comparing treatments, part one. What a treatment is basically when we apply um, some sort of variable to a product, person, whatever, uh, service. So we'll talk a little bit more about that. But what we're trying to do is we're trying to see if claims made can be rejected, or if we will not have enough information to reject those claims. One of the things you're going to find out in statistics is we don't prove anything. What we do is we say, hey, we reject this claim or we fail to reject this claim because we don't have enough information to reject the claim. So one of the instances here I have is a whole bunch of this like new and improved, and you can see it's been going on for a long time. New over here, is it actually really improved? This is kind of dubious here in the middle, and then new Coke, which if you want to hear an interesting story, look up the story about New Coke compared to Coca-Cola Classic and all that other kind of stuff. So first off, here's an example of a problem we're going to work through, and this is going to be for most of this topic 9, or topic 9 plus topic 10. It says a candle company introduced a new type of wax into their candles. They claim their candles burn longer than the leading brand. The burn times of 10 candles, 5 from each brand, rounded to the nearest hundredth of an hour, are shown below. The candles are the same height and width. They were burned in the same conditions. So we got all these different times. Now, this first part is going to seem really dumb. What we're going to do is we're going to take and randomly divide the candles into 2 groups using a random number generator, and we're not going to pay attention to the brand. So that seems a little bit silly. If you have, I know to a lot of you, if you had 5 candles of the old brand plus 5 candles of the new and improved, why not just burn all 5 of the old brands, then burn all 5 of the new brands, and then find out whether the new ones last longer. Well, that's just not the way we statistically do this because of replication. We want to be able to do this multiple times. All right. So what we're going to do is we're going to randomly split these up. So in group A, there's some of, the old brand and some are the leading brand and some of the new and improved. In group B, there's the same thing. And we don't know which ones are which. Like we really don't care. We're not paying any attention to that. All right. So the first thing that we're going to do is we are going to calculate the mean for each group. So of course, calculating the mean, it's very simple. We're just going to add these up. 12.15 plus 12.21 plus 12.02 plus 11.69 plus 12.14. And then there's 1, 2, 3, 4, 5. So whatever we get, we're going to divide that by 5. We're going to do the same thing for group B. Now to speed this up, I went ahead and did this on a calculator. So when we add up all of group A's candles, we get 12.042 hours. Again, it said this was hours. And group B is 11.916 hours. All right. So those are the 2 values that we get. Now, the next thing we're going to do is we are going to calculate the difference. And I've gone ahead and done that. So it says to calculate the mean of group A. When you see X bar, that's what this is called. That means mean. So the mean of group A minus the mean of group B, and we get 0.126. So that is the difference value. Now here it says to interpret the difference value in context. Basically, that just says, since this number is bigger, and that's with group A, that just means that the group A candles on average burn 0.126 hours longer than the group B candles. That's all that means. All right, what they mean by interpreting the difference. So here are some, it said the burn times were randomized 3 more times. In other words, what they did is they went back here and they rejumbled these candles up into new groups. And the next time they didn't get the exact same thing, of course, because it's just going to be random. So they got a value of 0.35. Again, if we were to interpret that, we would say that group A then burns 0.35 hours longer than group B on average. And then one time they got a negative. Now, how would we get a negative here? Well, if the group B average was more than the group A average, and you did group A minus group B, you are going to get a negative, right? So if this number here was smaller than this number, you would get a negative. So when we have that situation, this negative 0.21 means that group B's candles are burning an average of 0.21 hours longer than group A, all right? And finally, one more question. What would a difference value of 0 or very near 0 mean? So if this difference value was 0 or really, really close to 0, like 0.02 or negative 0.05 or something like that, that would mean that both groups of candles are burning about the same amount of time. Okay. Now it says we must consider that the observed differences in the means could be from chance or they could be statistically, and the word that we're going to put in here is significant. All right, significant. All right, so it might just be by chance that one group is burning longer than the other, or it might be significant. All right, statistically significant. In other words, far enough away from the center that, hey, this is not luck. This is really something. Okay. So what they did is we only had one randomization, but technically they said they redid it 2 or 3 times. It says, imagine that we randomized them and completed 249 more simulations. All right, that would be a total of 250 simulations. So what we have here is we have the difference values. So in the very center, we've got 0, and it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 times they added up, they regrouped the candles and they averaged them out, and there was no difference between the averages. While 3 times it appears there was a negative 0.01, and it looks like about 8 times there was a negative 0.2, 3 times there was a 0.02, that kind of stuff. And then a few times we had some really far out there changes. All right, a few times. All right, so it says determine if the following difference values are statistically significant. Now, in order to determine if something is statistically significant, if you remember right, when we had this whole, and you can see this is kind of normally distributed bell curvy shape, all right? So if you remember this bell curve that went like this, okay? In the middle, we had the mean, and then we had a standard deviation, a third standard deviation, and then to the left, we had 1, 2, 3 standard deviations. Remember, there was some data out here. If we wanted to, something was going to be significant, we needed to be outside of 2 standard deviations out. Okay, remember this was 95% of the data out here. So we were looking at stuff that was way out here as being statistically significant. Okay, so that ends up being about 5% of the values. Okay, so this is going to be our standard for whether something is statistically significant or not. Now, manually, this is a bit of a nightmare. It says determine if the following difference values are statistically significant. So they're asking us about 0.13. So if we go back to our dot plot, 0.13, well, this is 0.1, this would be 0.11, this would be 0.12, and this would be 0.13. So what we want to do is we want to find out how often a value this far out occurs. And what we would have to do is we'd have to check off each one of these dots. So we literally go through and count them. Now I'm going to count them, but I will speed this up in the video. So you won't actually see me counting all of these, or at least it'll sound like a chipmunk counting them, but I'm going to go ahead and do this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58. So 58 times out of 250, we got a value that was at least 0.13 or higher. Okay, so if we want to find out if that's statistically significant, we're going to take that calculation, 58 out of 250. I'll just throw that into a calculator. 58 divided by 250. And we get 0.232. So if we write that as a percentage, that's 23.2% of the time. So 23.2% of the time, remember, these values here were just completely jumbled up. All right? So 23.2% of the time, just by luck, we get a value that's that far out. So that tells us if we're using a 5% as our significance factor, that means we would want to get that value. We want that value to be out far enough so that we would only get it by luck or by chance 5% of the time. So 23.2% is well over 5%. So this value is what we call statistically insignificant. It's not far enough out for us to take note of. It's kind of boring. It's there's nothing going on there. There's nothing exciting happening there. So this value here, 23.2% or 0.232, statistically insignificant. It's not enough for us to declare, hey, guess what? Some really cool stuff's going on here. So now we want to check this one here, negative 0.24. So we'll go back to this list over here, and that's going to be over here. So here's negative 0.20 right here, right there. So this would be negative 0.21, 0.22, 0.23, and 24. So we'd only count this one. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that would be 12 out of 250. So we'll go back over here. So this is 12 out of 250. So if we get our calculator, 12 divided by 250, we find out that comes up only, remember, move this decimal 2 places. So that's be 0.048, or 4.8% of the time. Guys, this value is well out there, right? That's a very far away from center. So it only comes up value from here that way, only comes up 4.8% of the time when we just randomly jumble these up. That means this is a significant, this is statistically significant. These things that are out here and these things that are way out here just don't happen that often. Okay, so that's how we can tell whether something is statistically significant or not. There's 3 things that help us to determine if the difference value is statistically significant. The first is the difference value is relatively far from 0. Okay, it needs to be out far from 0. When we're talking about our data plots, the further we can get away from this, the better. Okay, now the second thing is, for positive differences, the percentage of observed values that fall at or above the difference is very small. What we mean by that, again, is the percentages that are out here, way out here, somewhere out here and up, are very small, right? In other words, they don't show up very often. And then finally, for negative differences, the percentage of observed values that fall at or below the difference value is very small. So again, that would be these values out here. How often do they show up? They don't show up very often. Okay, so we want to be outside of this big middle area right here. Okay, so you should now be able to do the check your understanding for section 12, topic 9, comparing treatments, part 1. But hold on just a second. Wait until I talk about this question at the bottom. There's a question that's kind of, I didn't like it. But remember, again, you have to make a valid attempt on the first attempt. Again, it should not take you 0 minutes, 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, even probably for that first one. Although I do think this topic 9 is somewhat quick. So, sometimes you have to do multiple sections, and yeah, it should take you longer, but make sure you have a good first attempt. All right. If you do get a failing grade, you should notice, hey, I got a 100 on that, but Mr. Lennon gave me a failing grade. Yeah, that's because you didn't take long enough. Okay. You'll have to contact me and I'll send you something else to do instead. So again, make sure you take your time on the first time. I said I can guarantee that fixing the failing grade will be a more difficult process than if you just did a valid attempt the first time. Okay. Now, if you do have a valid first attempt, you don't like it, all right, and you want to get a better grade, hey, go right ahead. Listen, I don't need you to fake extra time on future attempts. If you tried your absolute best, I've got students that take 20 minutes, 28 minutes, 38 minutes on their first attempt, and they get 2 out of 3 right, 1 out of 3 right, whatever, even 0 out of 3 right. At least they tried, okay? And then the second attempt, well, you already saw the correct answers. So you can go back, you can write down the correct answers as you're doing the first attempt, as long as you're trying, and then you do your second attempt, and it only takes you a minute or two. That's absolutely fine, or even less than a minute. I don't care about that. hopefully you can see why the answers were wrong, but it may not even time you on that if you're just reviewing. Now, one of the questions, and again, I don't know which one it is for you in this particular topic, is a bad question. I don't like the way they asked it. Well, the way they asked it is fine, but the way I look at it, the correct answer is not there. So again, I don't know which one yours is. It might be question 1, 2, or 3. It says the SATA data below measured the number of fruit snacks in a standard 8-ounce package. And I do believe there's multiple questions that uses data, so you got to be careful about which one this is. But it said random number generator divides the packages of fruit into 2 groups. The team computed a randomization 28 more times and represented the results in a dot plot below. So if you count this up, this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 23, 24, 25, 26, 27, 28 dots. Okay. Now, is the difference value of negative 0.33 statistically significant? Well, it's a little hard to tell, but I'm assuming that this is negative 0.3 right here. And then, you know, first off, I don't like this, so it's hard for me to tell if this is at negative 0.33 or not. I'm going to assume that it is. And if that's the case, this is 2 out of 28. Okay, so if we throw that into a calculator, and we get 2 divided by 28, we get 0.714. Now, 0.714 is 7.14%. That is not statistically significant, okay? This value is too great for it to be statistically significant. Now, here's the problem that we have. They asked us, is this statistically significant? And when you read through these questions, none of these really make sense. So the only one that to me made sense is no, because the probability of there being 0.33 less fruit, and that's what, when they say this is negative, well, actually that doesn't even work, because when we get a negative, that means there was more fruit in the less group. These two are the two that I were deciding between. I mean, this here doesn't make any sense at all. Yes, because the probability of there being 0.33 less fruit snacks in group 1 than group 2, that's true. But this isn't less than 5%, so you got to knock this out. All right, it was over 7%. All right, and then the last one, no, because the probability of there being 0.33 more fruit snacks in group 2 is less than 5%. Again, it wasn't less than 5%, so that leaves these two. But here's the problem. This one sounds all right, except for one thing. Here it says yes. Guys, if it's greater than 5%, that is not statistically significant. That is statistically insignificant. So if this were a no, then this would be the answer right here, okay? And this one says no, but the problem is group 2 does not have 0.33 less, because we get a negative value here. That means group 2 had had more fruit. Okay, so none of these work. This is the one that you should mark as correct, even though none of these answers are correct. This is going to be the one that's going to tell you. So find the one that says yes, find the one that says 0.33 more fruit in group 2 than group 1, and find the one that says greater than 5%. Mark that one as correct. Again, I know it's completely wrong, but guess what? There's no correct answer here. All right. So, part two, and this one's kind of interesting because we're going to use some statistical software, some technology here on this. It's a website that you can go to. So, same type of problem. We're still going to be doing this. So it says candle company introduced new type of wax, blah, 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 blah. The candles of the new wax had the following burn times. The candles of the leading brand had the following burn times. Now we're going to look at how we would carry out an actual randomized experiment for the data. So the first thing we want to do is we want to define the treatment group and the control group. The treatment group is going to be, we're going to call that the treatment group is going to be our new and improved. Okay, and the control group is going to be the leading brand. Okay, that's our control. See. Now it says to develop competing claims. When you take AP Stats, if you take it, we talk about the null hypothesis a lot. The null hypothesis claims there is no difference between the two groups. In other words, the new wet wax will not increase burn times. So it's going to be exactly the same or very close. The alternative hypothesis claims that there will be a difference between the two groups. So the new wax will improve or lengthen burn time. Okay. So, anyways, so it says write a difference value inequality that supports the alternative. Well, something to support the alternative. If we take the treatment group, all right, and we subtract from it the control group average, all right, well, we're saying that this should be more than this, all right? This should be more than that. So what we should get is a value greater than 0. So in other words, we only care if the burn times get longer so that we have a positive difference value. So we're going to completely ignore the negative difference value when we do this work. All right. So the next thing we're going to do is we're going to find the mean for each group and the difference value. And I went ahead and did that. So I took the values that were up above. All right. This is our treatment group. Added all 5 up, divide by 5, and we get a 12.092. Then our control group, 12.14, 12.02, add them all up, and we get this right here. So this is definitely longer than this, right? You can see that this is definitely longer than this, but again, we don't know if it's statistically significant or not. Sometimes by chance, we might just end up with the same exact values as they are right now. So we got to find out whether it's chance or not, okay? Now, we're going to take all 10 values. Now, remember, these here were actually all the new candles. These here were all the old, leading brand candles, all right? But now we're going to do what we did before. We're going to take those values and we're going to jumble them up, okay? Now, you can do this manually. It says you could write the 10 burn times on slips of paper, place them in a bag, draw out 5 slips for the first group, and then the remaining 5, find the difference value, then throw them all back in the hat and do that again a bunch of times. All right. If you notice, they did that 250 times before. Now, of course, I'm not going to have you do that, guys. What's the problem with doing that? Writing down, uh, all 10 times on the little strips of paper, throwing them in a hat, and then pulling them out. The problem is it just takes way too long. Okay, so instead we're going to use some technology to do this. All right, so we're going to use some technology. So the technology we're going to use is right here. It goes to a website. Okay, and if you want to type that in or just look up Rossmann Chance, and this is ANOVA Shuffle is the one that we're using, and it's called Comparing Groups. If you go to Google and you just type in Rossmann Chance, okay, and you bring this up, all right, it's going to be the one over here, all right, randomization test. If you go on that one, and we're going to change this in a minute, but currently we can't do it with the data that's here. But in a minute, we're going to do difference in means. But that's how you get to it. It's not that big of a deal. So what we want to do is we're going to clear out this data. All right. So we are going to type our data into this. And I'm going to be really fancy here now real quick so I can get my data on 2 screens. So I've got this is my treatment group, this is my control group, and now that I've got it like this, I can go ahead and type this in. It's very simple. You have to say, all right, I'm going to make the treatment group. Okay, so my treatment group has 12.25. And I just have to type in all of these numbers. Okay, so there's my 5 treatment values. And then I'm going to do the control group. And I'm just putting a space between each one. Oops. All right, so I've got my 5 treatment values in. This is just kind of a label. This is the labels that they'll put over here and over here. So that's all that will do. And I'm going to tell it to use the data, and you're going to see all this data change. This is the data that was in there before. So now you can see this is where my treatment candles were. This is where my control candles were. And we are going to change this to difference in means. Okay. And you can see we get our negative 2.26, which is something I actually didn't calculate over here yet. So, but if we did this number minus this number, I failed to do that, sorry, we would get 0.226. In other words, the treatment group burned 0.226 hours longer than the control group. Okay. Now, now we need to find out, and I'm going to make this big now. We're going to show some shuffle options. And it's asked us how many times do we want to shuffle this? Well, we want to shuffle this 250 times. Okay, so we just type in 250, and then you go ahead and hit enter, and it's just going to go ahead and, oops, I'm sorry, you hit shuffle responses, and it's going to go ahead and do that. All right, so it went ahead and did this 250 times. So what they did is it jumbled this up, these values, 250 times randomly. All right, first it jumbled them all up, then it ran the mean for each group and subtracted the difference, and then it continued to do that. Now sometimes we got values that were as low as, you know, wherever this is, it's a little hard to tell, and we had some other values are out here. Now again, we said we're trying to find out if the treatment candles last longer than the control candles. So we only care about greater than values. So that's what this thing here says, greater than. If they said we wanted to find out if something shortened the time of, you know, a recovery period, well, we might change this to less than. We might change this to not equal, different things. So we're going to leave greater than. The observed difference was 0.226. So that's what we're going to type in here, 0.226. And we're going to hit count. Now, we really don't care what comes up here. Now, if you actually do this, you will get completely different values than what I have. Remember, this is random, so you may not have this exact value here. That's okay, all right? But when I ran 0.226, only 19 of these 250 simulations came up with values greater than 0.226 as the difference of the means, okay? Now that's 0.0760, all right? So when we do that, let me see if it shows that on the next page here. So I got 0.0760, 0.0760, which is 7.6%. Now, guys, is this value statistically significant? Well, the question you ask yourself, is this less than 5%? And the answer is no. So if this is greater than 5%, that means this data that we got might just be somewhat lucky by chance that we got it. Again, it's not far enough away from the center. I know it's somewhat from the center, you know, we're way out here, but this is really kind of where our value is right here. And we're only just counting the ones above it. So no, it's not very lucky. It's still within the 95%. So that right there would tell us that our conclusion would be is that it appears that the burn time for the treatment and control group are relatively the same. All right, relatively the same. Okay, so, but look at this. Here's the data that we had before, but look what they found out. It was discovered that 2 of the values were interchanged. In other words, there was a problem, okay, with the values that we had before. So again, let me do the same thing that I did before. We'll put this over here, we'll put this over here, and let's see which one got changed. So we got, for the treatment group, we got 12.25, 11.89, and then we got 12.14, all right? And that 12.14 was not there before. So that means this 12.14 here and this 11.96 here, those 2 values got switched up, all right? So we're going to switch those, all right? So we're going to change this one to 12.14, and we're going to change this 12.14 to 11.96, okay? We're going to tell it to use this new data, all right? And then again, we're going to do the same thing that we did before. All right, we still want difference of means, and we're going to run this 250 times. We're going to go ahead and shuffle it. All right. Now, one thing that you do need to watch out for, notice this warning comes up. And it says your input does not match your original data. Remember, this 0.226 was our difference in means before, but remember, this was bad data over here. This 12.14 and this 11.96 got switched. We have a new observed difference here. It's 0.298. So we need to change this value to 0.298, and that's why that warning came up for us. So 0.298, and now we're going to go ahead and run it. All right, um, so now our 0.298 with our new count here, that count was 3 out of 250. And if you look at this, this is 0.120. So in other words, 1.2% of the time, value as far out as 3. I'm sorry, as far out as 0.298 is going to occur as a difference over means. So 0.012, again, that's 1.2%. That is definitely lower than 5%. So that would make this count statistically significant for sure. By the way, if you don't think 250 is enough, if you just keep hitting shuffle responses, you are going to see your counts add up. I just hit it 4 times, so now I've done 1,000 simulations, 1,000 jumbles, and now it's got 12 out of 1,000, which again is 1.2%. If I, pop it up a few more times, now it's 2,000 simulations, and I'm up to only, or I'm actually down a little bit, actually at 1.15%. So you can see that that is definitely statistically significant. So it's showing us here now that apparently the treatment candles, the new and improved candles, do have a longer burn time for sure, as far as the data shows us, than the control candles. Section 12, topic 10, comparing treatments, part 2, and you're almost done with this section and this video, because this last part is actually really kind of fast. Okay, so on to the last part. This is called interpreting data. We're going to take everything that we learned so far and we're going to do this for a scenario. So let's practice this. Is gas mileage affected by the brand of gas used? 90 cars were randomly assigned to brands A, B, and C gasoline. The resulting gas mileage was recorded in miles per gallon. So the cars or vehicles that were in gas brand A got an average of 18 miles per gallon. Gas brand B got an average of 25 miles per gallon, and gas brand C got an average of 16 miles per gallon. So how many treatment groups are there? Well, there are 1, 2, 3, A, B, and C. All right. How many subjects were in each treatment? Well, it said there were 90 cars. All right. And they were randomly assigned. So I would hope that each one would have 30 cars in it, right? 30, 30, 30. Okay. Do you think that's enough subjects for each treatment? Well, 30 subjects, yeah, that's enough. Remember, more data, would give you more accurate, information, but 30 is enough. There's one of the things that we do in stats is it always has to be greater than 10, and it has to be less than 10% of the population. So, but yeah, 30 cars in each group, that's fine. How are the subjects assigned to the treatment? Well, they were randomly assigned, and that's important, randomly assigned. Okay. And do we see any issues with this design? Well, one issue that I see is these could be different kinds of cars. So maybe you had, maybe it was a fleet of vehicles. For instance, like maybe the school district was doing this, and some of these in this group might be buses or trucks, and some of this in this other group might be smaller cars, and that might explain why this group got better gas mileage than that group. So that is something that maybe is an issue here. And it says newspaper reporters came up with some titles for this experiment. Which one is the most appropriate? A certain brand of gas results in better gas mileage. Cars help improve gas mileage, or people can get better gas mileage for their car. I think that we would probably go with this one right here. People can get better gas mileage for their car. That could be anything. And then cars help improve gas mileage. Yeah, I don't think cars do that. Um, All right, so here it says if you flip a coin enough times, it should land on heads 50% of the time and on tails 50% of the time. Take a coin and flip it 40 times. Guys, I actually did this. I did. I actually did this. And I recorded it. And guess what I got? I got 23. It says, how many times did the coin land on heads? I got heads 23 times out of 40. That was my experimental probability. Okay. Now, of course, we would think it would 20 heads, 20 tails, but again, that's not going to happen all the time. It says, how close is your proportion to the theoretical result of 0.50? Well, if I throw this into a calculator, 23 divided by 40 gives me 0.575. So I got heads basically 57.5% of the time. All right. So I got heads. Let me write this down. 0.575 or 57.5% of the time. So now we want to calculate the margin of error for this. Well, the margin of error, remember, there's this formula, we call it p hat, all right, times 1 minus p hat over number of samples, take the square root, and then we multiply that times 2 to get a 95% confidence interval. So the p hat is 0.575. 0.575. The 1 minus this would be, let's see, that would be 0.425 over, how many times did we flip this coin? 40 times. So let's just run this in the calculator. All right, so we got 0.575 times 0.425. We get this value. We're going to divide that by 40. We're going to get this. We're going to take the square root of that, and then we're going to multiply that times 2. And I get let's say 0.156. Let's just go with that. All right, 0.156. So my experiment was 0.575 plus or minus my margin of error, which again was 0.156. Okay, so let's see if that's reasonable. Again, we would think there's something called the law of large numbers. We would think that the true proportion or theoretical would be 0.50. So let's see if this is valid. Okay, see if this is reasonable. Well, if I take my calculator out and I do 0.575 and I subtract from it 0.156. Oops, 0.156. I get 0.419. So 0.419, which is 41.9%. If I take this value and then add this to it, 0.575 plus 0.156, I get 0.731, which is 73.1%. So basically what we're saying is the true amount of times that when you flip a coin you get heads should be somewhere between 41.9% and 73.1%. Well, 50% is definitely somewhere in that range. So yes, this is reasonable. Okay. Now, if you perform this experiment, you would get different values. And I know some of you guys, but hopefully you should still capture that 50% somewhere within this range. Now, I know that some of you guys look at this, you go, yeah, Mr. Lang, this is stupid. That's like saying, you're going to get heads when you flip a coin between 0 and 100% of the time. Yeah, but this is when we only did this 40 times. If you did this experiment many, many, many more times, this would tighten up. Okay, so if we did this experiment 400 times, just to show you one time how that is, if I threw that into a calculator, you can see how much that's going to narrow down this margin of error right here. That's going to change a lot. It's going to get a lot smaller. So if I did it 400 times, that would be 0.575 times 0.425 divided by, let's say, 400 this time, and then take the square root of that, and then times 2. Guys, look how small that margin of error got now. It's only about 5%. all right, where before it was 15.6%. So, yeah, when you perform more experiments, when you get more data, you get more accurate data. That's how all this works, all right? And so this is the last part of this. In the last election, one of the states reported a close race. In a recent poll of 100 people from the state, the Democratic candidate had 47% support, while the Republican candidate had 45%. The margin of error for this poll is 5%. So, what is meant by the margin of error of 5%? Well, what that means is this particular person's support can be anywhere between 47 minus 5% and 47 plus 5%. So it could be anywhere between 42 and 52%. All right. So the Democratic candidate, all right, we put DEM, their support is somewhere between 42% and 52%. And the Republican candidate, they had 45. So their support is somewhere between 40%, this is 45 minus 5, and 50%. Somewhere in between there. That's 45 plus 5. So it says, what are some of the reasons why the percentage of the two candidates might not add up to 100%? Because 47 plus 45, that's only 92. Well, maybe there's a third party candidate, somebody else out there running, or maybe some of the people that they polled, the 100 people, they said, I don't support either one. All right. So, or maybe they didn't know. There could be lots of reasons for that. And finally, part C, upon further reading, the results of this poll can be said to be a toss up. Why would these results be interpreted in such a way? Well, again, if you look at the ranges here, all right, for those people, um, we call this a toss up because there's overlap, all right? So, anytime you have any sort of overlap where there's areas, so for instance the Republican person, they go from 40 all the way up to 50, all right, while the Democratic person goes from 42 all the way up to 52. And this area in here, this overlap, this is where the uncertainty lies, right in here. Okay. So since, they have that overlap there, that's why we're going to say it's a toss up. We don't really know who's going to win, even though it appears that the Democratic candidate has the advantage in this particular race. And that's it for the statistics module, other than some sort of an assessment that I'm going to be getting to you soon. We'll figure that out. It'll be next week. This may be, if you look at that, it said this may be your last assessment for the school year. We just have to look on time. So you want to do your best on this assessment as you can when it does come out. And I'll let you know what to do for that. But currently, that should be the end of your statistics module. All right, guys, have yourself a great week. Please make sure that you have a valid first attempt on your topic 9, 10, and 11. Check your understanding questions on Math Nation. All right, guys, again, have a great week. See you guys later.